Welcome to the Organic Chemistry Podcast, or Dr. Brian Lloyd's Scribblecast. The first homework problem assigned in the course was in the area of electron configuration. You were asked to calculate the atomic number of the neutral element that will place one electron in a g-subshell. The reasoning behind this question was so that you might better understand why we talk about the periodic table in terms of s, p, d, and f orbitals only. Why not in the case of the g-subshell? Why don't we mention the g-subshell? In order to do this, we need to write down our subshells in descending order. Now, you should note that the first shell can have only one subshell, the 1s. The second shell, as we've learned, can have two subshells, the 2s and the 2p. The third shell can have three subshells, the 3s, 3p, and 3d. The fourth shell can have the 4s, 4p, 4d, and 4f, or 4 subshells. The fifth, as you might guess, can have the 5s, 5p, 5d, and 5f. And after f, we start with the normal alphabet, G. The sixth can have 6s, 6p, 6d, 6f, 6g, and 6h. The seventh shell has the 7s, p, 7d. I'll stop at 7d. And by the time you get down to the 8, you've got the 8s, and you've got 8 potential subshells. Now, in order to get the proper energy ranking for a neutral atom, and what works for most neutral atoms, we draw diagonal lines through our list here, thusly. And if we want the proper ranking in terms of energy so that we fulfill the Aufbau principle and fill lowest energy orbitals first, we just follow the diagonals in the order they appear from top to bottom. So the first diagonal hits what is the 1s subshell. The second diagonal hits the 2s. Then we have the third diagonal hitting the 2p and 3s. The next diagonal hits the 3p and 4s. Next diagonal hits the 3d and the 4p and 5s. Interesting to note, of course, is that 3d is higher energy than the 4s. And so we find that the shells don't just follow an energy 1, 2, 3, 4. There is some variation here that's coming out in this pattern. Now, after 5s, we go to the 4d, the 5p, then the 6s. After 6s, we have 4f, we have 5d, 6p, 7s. After the 7s, we jump up to this last red diagonal, 5f, 6d, 7p, 8s. And if we put in the last diagonal, it's only afterwards that we hit the 5g. After all of this, we finally hit the 5g. Now, if you remember, each subshell could be divided into orbitals. S subshells only have one orbital. P subshells have 3 orbitals. D's 5. Notice we're increasing by 2 every time. F 7. And then G's 9. Now, each orbital can hold 2 electrons, so the S's can all hold 2 because there's just one orbital. P's with 3 orbitals can hold 2 electrons each, that's 6. S can hold 2. Notice we're filling the lowest energy first. D has 5 orbitals. Each can hold 2 electrons. That's 10 electrons. P is 6. S is 2. D is 10. F is 7 orbitals, each with 2 electrons. That's 14 electrons. D 10. P 6. S 2. 14. 10. 6. 2. Now the question states the atomic number of the neutral element that will place 1 electron in G subshell, so let's put 1 in our G. Now let's add this up. 2, 4, 10, 12, 18, 20, 30, 36, 38, 48, 54, 56, 60, 70, 80, 86, 88, 98, 102, 112, 118, 120, 121. The atomic number, well, hold it, this is electrons. Well, remember, to be a neutral element, you must have in the nucleus a number of positive charges equal to negative charges. If this electron configuration is the number of negative charges I have, then it must equal the number of protons in the nucleus. The number of protons is the atomic number. Hence, the atomic number for the first, or for the neutral element that will put 1 electron in the G subshell is 121. Now take a look at your periodic table. If you check the most recent periodic tables, you will find elements 114, 118. Realize we're not there yet. It's for this reason that sometimes in textbooks you will find them referring to the periodic table as consisting of S, P, D, and F orbitals, and not G. Well, there you have it. I thank you very much.